So in this video we're going to be looking at Newton's second law of motion. And Newton's second law of motion, as stated in the subject outlined by Sayce, is that if an unbalanced force acts upon an object, then that object will accelerate in the direction of the net force. Very logical. Now this can be mathematically given as the force applied is equal to the mass of the object times by its acceleration. And you're going to need to be able to solve problems involving this equation. And we're also going to look at the difference between mass and weight. And why in physics they're very different words, whereas in everyday life they're basically interchangeable. So, basically Newton's second law of motion. So, the net force of an object is equal to the product of the mass and its acceleration. You can think of it as force equals mass times acceleration. Another way to think of it is if we rearrange it into acceleration equals force over, if we rearrange this, divide both sides by mass, we get acceleration equals force over mass. So we get acceleration equals force, I don't know what's going on right now, force over mass. And then this helps us think about it in this way. So the acceleration is caused when there's a net force on an object, right? So there's an imbalance of forces. And if we look up here, acceleration is directly proportional to force. So acceleration is directly proportional to force. That means directly proportional. So we'll look at it on a different slide. So acceleration is directly proportional to force. I'll look at it on this slide. So acceleration is directly proportional to the force applied. So if we have this skater and we have, let's just say he's a mass, let's just say he's 50 kilos, he's a boy. He's 50 kilos and some force is being applied. Now, if this force is only this strong, then he's going to accelerate at this acceleration. However, if we double the force, right, and his mass stays the same, then we're going to double his acceleration. Right? Because acceleration is directly proportional to force. If we tripled the force, he'd have triple the acceleration, and so on and so forth. If you were to push an object on a desk, the larger the force you apply, the greater the acceleration of the object it's going to be. It's pretty logical. The second thing we need to know is that acceleration is inversely proportional to the mass. So it's inversely proportional to the mass. And what this means is that now we have skater again, except this time we have a skater that is half the mass. So it's a real tiny little girl. Say she's half the mass, so I don't know, 25 kilos. Now if we apply the same force to both these skaters, right, and she's only got half the mass, she's going to accelerate with double the acceleration. Whereas he's only going to accelerate with that normal acceleration. So, but you can think of it like if you try and apply the same push, the same force, strength force, to two objects, the heavier object is obviously going to have less acceleration, and the lighter object is going to have more acceleration. It's logical. So acceleration is inversely proportional. Acceleration is inversely proportional to mass, which means as you increase mass, the acceleration will decrease. Now, you need to know that, say, force is equal to mass times acceleration. Force is measured in a unit called newtons. So capital N is the unit of force. Mass is always in kilograms. So if you ever get it in grams or tons, you need to convert it to kilograms. And acceleration is always in meters per second, or meters per second squared. And you need to be able to rearrange F equals ma. I'm pretty sure this is the one that's on your formula sheet. You need to be able to rearrange it to this and this. So to get acceleration, you're just going to divide both sides by mass, and it'll be force over mass. And to get mass, you just need to divide both sides by acceleration, and you'll get acceleration equals mass equals force over acceleration. So, cover those sides. So as I said, when mass is in kilograms and acceleration is in meters per second squared, then the unit of force is newtons. And what actually is 1 newton? Well, if force is equal to mass times acceleration, 1 newton is equal to the force required to move a 1 kilogram mass at an acceleration of 1 meters per second squared. Okay, or it's the force required to accelerate a 1 kilo mass by 1 meters per second for every second. Now, another really key important thing is, what is the difference between weight and mass? So, they are very different things. Basically, we use them interchangeably in everyday life, but I want you to think about it like this. So, the mass of an object is purely just the amount of matter it has inside of it. How much little atoms are packed inside the object. Okay? So, and what weight is actually a force. Weight is a force, and it is the force due to gravity. So, gravity applies a force, right, on another mass, and we refer to the force due to gravity as weight. So, realistically, in everyday life, when you say you weigh 70 kilos, you actually have a mass of 70 kilos, and your weight is actually completely different. It's the force due to gravity. So, the force due to gravity, I'm just going to use little g as a subscript. So the force due to gravity is the mass of the object times by acceleration. And we know that the acceleration due to gravity on Earth's surface is constant, and it's just g, which is 9.8. G is 9.8. G is equal to 9.8 meters per second squared. So, in order to calculate the weight of something, which we'll do on next later slide, in order to calculate the weight of something, okay, the weight, you can sometimes use capital W for weight equals mg, or the force due to gravity equals mg. And so your weight is actually your mass multiplied by 9.8, the acceleration due to gravity. So, would the mass of an object be altered by location? No. You have the same mass, so you have the same amount of matter, no matter where you are. Okay? However, so mass is related to how much stuff there is, the amount of kilograms, and weight is the amount of pull due to gravity on the stuff. So, the mass of an object is altered by location. So if you're on different planets, so like the moon has a very much weaker acceleration due to gravity on the moon. So your weight actually changes when you go to different locations based on the gravitational pull. So just a quick little example question. So if a melon weighs 1 kilogram, its weight would actually be, so remember, force due to gravity, or weight, is equal to mass times gravity. So it would be the mass, 1 kilo, times 9.8. So it would be 9.8 kilograms. And now the apple, well, obviously mass. So if you want mass is weight divided by gravity. So the mass of the apple would be 0.98 divided by 9.8, and it would be 100 grams, or 0.1 kilos. The dog, it would be 25 kilos. The weight. The weight would be mass times gravity, and 25 times 9.8 is 245 newtons. And then lastly, 980 newtons. So mass is weight over gravity. So the weight is 980 newtons divided by 9.8, so it's 100 newtons. Now, how much force is needed to accelerate a 14... So how much force, so we're looking for force, is needed to accelerate a 1400 kilogram car. So the mass is 1400 kilos. And the acceleration is 2 meters per second squared. So what force is required? Well, force is just mass times acceleration. So it's just 1400 times by the 2. And then that's going to give us 2800 newtons. So generally, have your units in newtons for force. Now, I'll just pause it here and just fill in the few blanks in this table. So remember, F is equal to mass times acceleration. Acceleration is force over mass, and mass is force over acceleration. So I just want you to pause it and just fill out the few blanks. So hopefully you got 4 kilograms, because the mass is just force, 20 divided by 5, which is 4. And then hopefully for acceleration you got 10 divided by 5, which is 2 meters per second squared. And hopefully for force you got 1 times 10 is 10. So obviously if mass remains constant, then doubling the acceleration will double, in order to get double the acceleration, you needed to have doubled the force. If force remains constant, then if you doubled the mass, the acceleration would be halved. Now, Newton's second law of motion helps to prove that even though different masses, proves that different masses all accelerate down to Earth at the same rate, but with different forces. So if we look at a 10 kilo mass, the force due to gravity pulling on it, remember, is mass times acceleration. The force due to gravity is mass times gravity. Which is the 10 kilo mass. Oh, my PowerPoint's gone nuts. Is the force due to gravity is mass times acceleration, so it's the 10 kilo mass times 9.8. So it's a 98 Newton force pulling down on this 10 kilo rock. Okay, and we know the acceleration is force over mass, so it's the 98 Newton force pulling it down over the mass of the object, which is 10. And so the acceleration pulling down on the rock is 9.8 meters per second squared. And on a 1 kilo rock, because it's less mass, the force due to gravity is only 9.8 newtons, because the force due to gravity was only the 1 kilo times by the acceleration, so it's 9.8. And basically then the acceleration on this rock is also just the 9.8 divided by the 1 kilo, so it's accelerating down to Earth at 9.8 meters per second squared. Now there is another way to calculate the force due to gravity using a much more complicated formula, using this, and it gives the same force due to gravity, and if we measure it experimentally, it's always the same. I'll show it. So basically the force due to gravity between two objects is the product of the masses and divided by the distance between them squared and some special constant, and this gives the same value. So two objects, even though they have different masses, because of those different masses they have a different pull due to gravity, but then because they do have the larger mass, they're going to accelerate at a lower acceleration. They're going to accelerate at the same acceleration. But they do hit the ground with much different forces. Now, this is just calculating net forces. So which of the following would have the greatest acceleration? Well, A would have a net force of 6 newtons to the right. This would have a net force of 9 newtons to the right. This would have 6 newtons. This would have 3 newtons. This one would have 6 newtons. and this one would have 3 newtons. So which of the following would have the greatest acceleration? Well, we know that acceleration is force over mass. So this first one would be, the acceleration of this first one would be force, which is 6 newtons to the right, over a 2 kilo mass. So it would be 3 meters per second squared to the right. This next one would be, acceleration would be 9 over 3, so it would be 3 meters per second squared to the right. This one would be acceleration equals 6 over 3, so it would be 2 meters per second squared to the right. This one would be a 3 newton force, so the acceleration would be 3 newtons over 3 kilos, so it would only be 1 meters per second to the right. This one would be a 6, so acceleration would be the force applied, which is 6 newtons, over the mass, which is 2, so it would be 3 meters per second squared to the right. And this final one would be, acceleration is the force applied, the net force applied, remember, sorry, which is 3 over 3, which is 1 meters per second squared to the right. So which of the following would have the greatest acceleration? So it would be A, B, and E. So what I want you to do now is, just to check your understanding, just do a quick few calculations. So pause it on this slide, do the quick few calculations. So calculate the acceleration, calculate the mass, calculate the force and the force. And then pause it and have a go at these questions. So hopefully you had a go at them. So those are the answers on your next slide. Hopefully you got them all right. Let me know if you didn't. This is the last problem that we're going to go through. So sometimes you can have forces in different directions acting. Now, a kind of force that I haven't really talked about is a normal force. So imagine that so an applied force of 50 newtons, is used to accelerate an object to the right. So someone's pushing on it to the right at 50 newtons, and it's accelerating the object. Now it is a frictional surface, so there is a force due to friction. Let's just say it's on a tabletop, so there is a force due to friction. So use the diagram to determine the normal force, the net force, and the acceleration of the object. We're going to neglect any resistance due to air. So first things first, I want to talk about the normal force. So whenever anything is resting on a tabletop or the ground, there is an equal and opposite force applied. Now we're going to talk about this is Newton's third law, but I'm just going to introduce it here basically. So whenever an object is resting on a tabletop, there is a force due to gravity pulling it down. That's why it's resting on the tabletop. Now there is an equal and opposite force applied upwards on that object, in order to keep it balanced on the tabletop. And that force we refer to as the normal force, and it's always opposite in direction, completely opposite, but equal in magnitude, so equal in size, so it's an 80 Newton force. Now, on this object, someone's pushing it with a 50 Newton force to the right, and a friction is opposing it 10 newtons to the left. So the net force acting on this object is going to be 40 newtons to the right. Now, the mass. We need to work out the mass of the object. Well, we can work out the mass of the object because force due to gravity. Oh, sorry, I don't know what is going on. The force due to gravity, or the weight, is equal to mass times gravity. Right? So we can work out the mass of the object because it's the force due to gravity divided by the acceleration due to gravity. So the mass of this object is the 80 Newton force divided by 9.8. So 80 divided by 9.8 is equal to 8.16 to three significant figures. So 8.16 kilograms. Now, the acceleration, we know that acceleration is equal to the net force over the mass. The net force we just worked out was 40 newtons. So the acceleration on the object is going to be the 40 newton net force to the right over the mass of the object, which is 8.16. If we do 40 divided by 8.16, we get a acceleration of 4.90 meters per second squared to the right, and that's to the right as well. So acceleration and force are vector quantities. So force is a vector quantity. It has both a magnitude and a direction. Alright, I now want you to complete some practice problems. Thanks for watching.